At the hardware level, a single physical CPU core can execute exactly one instruction thread at any given microsecond. That is a strict physical limit. What we experience as concurrency is an illusion. The operating system rapidly alternates processor time across multiple tasks, creating the perception of simultaneous execution. This diagram details the context switch. To pause one thread and start another, the OS saves the current thread's registers and program counter to memory, then loads the next process. This carries a severe penalty, consuming between 5,000 and 20,000 CPU clock cycles. This is distinctly different from true parallelism. Parallelism requires multi-core hardware, where distinct CPU cores handle distinct threads simultaneously, completely bypassing the switching overhead. Because developers often treat threads as cheap, lightweight language features, they routinely overallocate them. This unintentionally triggers massive context switching penalties that degrade system performance. Mastering Java concurrency does not mean spawning the maximum number of threads. It requires structuring code to respect the steep silicon-level cost of operating system task switching. Moving up to the Java virtual machine, invoking the new_thread constructor only allocates memory for a standard Java object. It does not create an actual executing thread. This diagram maps Java to the native OS. Calling run directly loops back synchronously, blocking the main thread. Invoking start crosses the native interface boundary, triggering the start0 C++ method. This native method reaches the OS kernel, allocating a physical POSIX thread. Once that one-to-one mapping is established, the Java thread enters a queue, where it must wait for the operating system scheduler to grant it a slice of physical CPU time. Java thread management is tightly bound by native OS scheduling rules. You are effectively piloting OS threads. Historically, developers would subclass thread and hardcode business logic directly inside it. This tightly couples the task definition to the execution mechanism. The modern architectural standard solves this by decoupling the execution mechanism from the task definition, represented by the runnable interface. However, runnable cannot return a value. For tasks requiring a return payload, Java provides the callable interface. This UML diagram illustrates the architectural bridge. Thread only accepts runnable, not callable. Future task acts as a wrapper, implementing runnable so it can execute in a thread. Simultaneously, it implements future, allowing the parent to invoke get to capture the return value. This timeline shows the synchronization cost. Invoking get or join transforms an asynchronous execution into a synchronous block. The calling thread freezes entirely until the calculation completes. Decoupling tasks from threads allows the JVM to safely pool and reuse expensive OS threads. To manage these decoupled threads safely, the operating system utilizes a strict 5-state lifecycle, tracking tasks from initial to terminated. This schematic details how the JVM abstracts underlying OS complexity into a 6-state machine. Notice the runnable state at the top. The JVM deliberately merges the OS states of ready, waiting for CPU, and running, executing on the CPU, into this single Java state. The JVM cannot predict exactly when the OS scheduler will pull a thread onto the physical CPU. From the JVM's perspective, the thread is simply ready to run. A thread leaves this state when it is blocked by a monitor lock or waiting for an explicit signal. Timed waiting operates similarly, but it will automatically resolve after a set duration, which is typically triggered by invoking thread.sleep. Developers can optimize scheduling using thread.yield. This command voluntarily moves a thread from running back to ready, allowing it to yield CPU time without ever leaving the JVM's runningable state. When multiple threads attempt to initialize a concurrent hash map, only one is permitted. The others must wait. Instead of putting the waiting threads to sleep, which would trigger a heavy context switch into timed waiting, the architecture uses yield. This minimizes overhead. The JVM hides OS volatility. Tools like yield help developers manipulate scheduling and avoid context switch bottlenecks. When managing a thread's lifecycle endpoint, Java developers are strictly forbidden from using the stop command. Executing stopping immediately throws a thread death exception. It violently forces the thread to release all monitor locks it currently holds, regardless of the operation's progress. Thread A holds a lock to transfer $100. It successfully decrements account 1. If stop is called before account 2 is credited, the lock shatters. Account 1 is short, account 2 is unmodified, and a new thread can instantly read this corrupted state. This dictates an absolute rule of Java concurrency. Thread management must be cooperative, never coercive. The safe alternative is interrupt. It does not force a shutdown. Instead, it sets a Boolean flag, politely signaling the thread to wrap up its task, release its locks gracefully, and exit. High-performance Java concurrency relies on respecting hardware limits and decoupling execution models. True safety at scale requires cooperative state management, allowing the system to handle complexity without coercion.